I'm William Cooper. In 1/6 gravity, everything would weigh 1/6, or 16.7% of its earth weight. In other words, a 180-pound man would weigh a mere 30 pounds. Think about this, ladies and gentlemen, because I'm going to strip away some of the bullshit that NASA's been shoving down your throats for years. Writers were speculating on the athletic abilities of men on the moon a long time before the space program and Apollo. They based their calculations on 1/6 gravity, because that's what the scientists told us the gravity on the moon would be. And the public was anticipating some of these spectacular athletic feats when astronauts explored the moon. Do you remember seeing any? None were ever performed, ladies and gentlemen. There just weren't any. And you say, well, they were weighted down with these big, giant, heavy suits. I got a bridge. You want to buy it? You may remember the televised pictures of astronauts moving around on the moon's surface. If so, we challenge you to recall any extraordinary feats at all. Because in all actuality, ladies and gentlemen, there were absolutely none. Zero. Zilch. Zip. Nothing. In the November 1967 issue of Science Digest, an article appeared by James R. Barrie entitled, How to Walk on the Moon. In it, Mr. Barrie predicted that men would be able to make 14-foot slow-motion leaps, perform backflips, and other gymnastics just like professionals, and be able to easily move up ladders and poles with their arms, not even having to use their feet. Another prediction was given in 1969 by the writers of U.S. News and World Report in an article entitled, U.S. on the Moon. Look it up. And they said, with gravity on the moon only 1/6 as strong as it is on Earth, a home run hitter in a lunar baseball game could drive a ball well over half a mile. A golfer's drive from the tee would sail clear over the horizon, out of sight. You wouldn't be able to see where it landed, even if you wanted to. See, the height an object will rise in a gravitational field, ladies and gentlemen, depends upon its initial velocity. And if an object had the same initial velocity in 1/6 gravity as it had on Earth, it would rise 6 times as high. If the initial velocity of the object were doubled over its Earth velocity, it would rise 24 times as high. And if tripled, it would rise 54 times the Earth height. Imagine the golf tournaments in such an atmosphere. A man jumps vertically by bending his knees and then flexing his thigh muscles to full extension. Try it yourself, right where you are. Get the feel of this so you'll know exactly what we're talking about. You see, when he does this, it propels him off the ground with a given initial velocity that can be measured. And if an astronaut were to jump vertically in 1/6 gravity with the very same effort expended on Earth, the initial velocity would be greater than on Earth. Therefore, the astronaut would go more than 6 times higher. And we haven't even gotten to these suits yet, so don't get ahead of me. We're going to cover that, folks, using NASA's own figures. You see, for the purposes of this broadcast, a conservative approach is taken, and I always do that with anything that we talk about, simply because I know that the wolves are out there ready to jump. We take a conservative approach in determining the relative jumping ability of astronauts in 1/6 gravity versus Earth gravity. A complicating factor, folks, is the alleged weight of the spacesuits and backpacks worn by the astronauts. Now here's where the fun begins. You see, NASA claimed, it's their own figures. I didn't make this up, and you can check yourself. NASA claimed that the gear weighed 185 pounds. Let me repeat that so that there's no misinterpretation. 185 pounds. Now this is a terribly oppressive weight to carry on the earth. But folks, it would be no problem whatsoever in 1/6 gravity. That is, assuming that the astronauts weighed 185 pounds and their gear weighed the same. And these are the NASA figures, and the astronauts, all of them, weighed pretty close to that figure. The total combined weight, ladies and gentlemen, in 1/6 gravity would be only 62 pounds. Now just ruminate on that a little bit. If the astronaut weighed 185 pounds, and his entire suit, all of his gear, weighed another 185 pounds, the equivalent combined total weight in 1/6 gravity would be only 62 pounds. And I'm here to tell you I could do amazing things if I weighed 62 pounds anywhere. Anywhere at all. But we didn't see any of that, did we? You see, this is still only 1/3 of an astronaut's body Earth weight, without any gear. Are you beginning to understand? Therefore, the astronauts should have been able to jump vertically far higher than they could on Earth without any burden. And you remember when they were tooling around in that little car and they were spinning their wheels and the dirt was flying up, making a rooster tail? Well, folks, that dirt didn't fly up very high and it didn't stay up in the air. It came down really quick. And according to statistics, dust in a 1/6 gravity atmosphere. In fact, an atmosphere only 2% as dense as Earth's atmosphere, that dust should still be floating around somewhere, shouldn't it? But it didn't. How are we going to explain this? How does NASA explain it? Very simply, folks, they don't. They can't. They never could, and they never will. Quite a number of professional athletes, ladies and gentlemen, can jump over 3 feet off the ground when they are stretched out, such as in a basketball layup. These athletes are the exception. But an average man in good condition can easily manage 18 inches in a standing vertical jump. Try it in your living room. Try it right now. I don't care how much you weigh. If you can't reach 18 inches, there's something really seriously wrong. Like you might be permanently injured and trying to jump from a wheelchair. It can be assumed that the astronauts, ladies and gentlemen, were capable of attaining this on Earth with a moderate effort, especially considering the rigorous training and the physical condition which they were expected to maintain. And in fact, if they did not maintain that certain specific physical conditioning, they would not have been allowed to make their flight. Are you following? Clear, crystal crisp logic that only comes from the hour of the time. And finally, folks, since John Young's vertical jumping during the Apollo 16 mission has been observed on film many times by all of you and by me, the question of spacesuit mobility and height attained can be discussed because we've all seen it. You can go down and rent videos from your local video rental store right now and watch it again. You can order videos from NASA. You can do all of these things. You see, a standing vertical jump of at least 18 inches on Earth can be accomplished by exerting an upward force of around 500 pounds by a 185-pound person. An equation can be derived which gives the relative heights attained by an astronaut in 1/6 gravity carrying a burden equal to his weight, and the same astronaut on Earth without a burden. Now, it was assumed that in each case the upward forces were identical, since a jump from a standing vertical position only requires the knees to bend slightly. the spacesuits would not have hampered the astronauts appreciably. The televised pictures of John Young on the moon indicated that he was able to utilize his arms and legs for jumping in an essentially normal manner with very little, if any, restriction. Now, folks, this is where it gets very interesting. You see, the resulting ratio of relative jumping ability calculated turns out to be over 4. Over 4. Now, this means that even with the astronaut gear, Young should have been able to jump over 6 feet off the ground if the moon had 1/6 of the Earth's gravity. Now, let's be conservative. Let's say he should have been able to only jump 3 feet off the ground in 1/6 Earth's gravity. Did he? Not on your life. In actuality, his efforts lifted him at most, ladies and gentlemen, 18 inches off the ground. Observations indicated that Young made several attempts to jump as high as he could, but with no success in achieving a height of more than 18 inches. He is shown at the peak of one of his jumps in one of the famous NASA photographs. And if you can obtain this photograph, you will note the position of the top of Young's helmet in relation to the flag. Now, critics might claim that he wasn't really trying. Now, if you were on the moon and you had a chance to make a record jump and you knew that you were being viewed on television by billions of people around the world, are you trying to tell me that you wouldn't really try? Really? Is that what you're trying to say? Do you expect me, William Cooper, to believe such blithering nonsense? Because I don't believe it for 1 second. I think Young was trying the very best that he possibly could. You might claim that he purposely kept his jumping efforts to a minimum. But if this were the case, ladies and gentlemen, a similar Earth effort without a backpack and suit would have lifted him only 5 inches or so. And this was probably Young's last chance to demonstrate that the moon had a low surface gravity. Why on earth wouldn't he make a reasonable effort to impress the world by jumping at least 3 or 4 feet? Especially when the figures say he could have easily reached 6 feet off the ground in a 1/6 gravity. You see, a reasonable jump would have been conclusive proof that the moon had a low gravity, and the risk of injury would have been minimal in low gravity conditions, even with the backpack and suit. With the knowledge that the astronauts could only jump about 18 inches on the moon, and assuming that the gear weighed what NASA claimed, and assuming that they were really on the moon when they made this jump, which is quite an assumption based upon all the evidence that we've been able to gather here.
Well, in my left hand I have a feather. In my right hand a hammer. And I guess one of the reasons we got here today was because of a gentleman named Galileo a long time ago who made a rather significant discovery about falling objects in gravity fields. And we thought that where would be a better place to confirm his findings than on the moon. And so we thought we'd try it here for you. The feather happens to be appropriately a falcon feather for our falcon. And I'll drop the 2 of them here, and hopefully they'll hit the ground at the same time. How about that? This proves that Mr. Galileo was correct in his findings.
Dropping the hammer and the feather, and sure enough they both fall together, and that proves immediately that this experiment was done in a vacuum. So this movie set would have to have been evacuated. It would have to be a vacuum. But more than that, the 2 objects fall slowly. They would fall 6 times faster on the Earth because the gravity is stronger. You see them fall slowly on the moon.
And so we thought we'd try it here for you. The feather happens to be appropriately a falcon feather for our falcon. And I'll drop the 2 of them here, and hopefully they'll hit the ground at the same time. How about that?
This is also a very difficult image to fake.
Well, actually, it isn't at all difficult to fake. NASA itself would repeat the very same trick, this time officially in the 1999 story From the Earth to the Moon. This time the actonaut held the hammer the other way up, so that we could see it was not the same fakery as the first time. Of course, that original demonstration by Apollo 15 doesn't in any way prove that it had taken place on the Moon. Before NASA reenacted the whole thing officially, we had already conducted our own experiment. Here we are in our London studio in 1G, complete with an atmosphere, and without the benefit of a vacuum chamber. There they go. As you can see, the feather and the hammer arrive on the ground at the same time. Now if we slow it down by the appropriate amount, lo and behold, these two items fall nice and slowly as per a 1/6 G environment. This illusion is all about calibration.
Well, in my left hand I have a feather, and in my right hand a hammer, and well, I guess one of the reasons we got here today was because of a gentleman named Galileo a long time ago who made a rather significant discovery about falling objects and gravity fields. And we thought where would be a better place to confirm his findings than on the Moon. And so we thought we'd try it here for you. The feather happens to be appropriately a falcon feather for our falcon, and I'll drop the two of them here, and hopefully they'll hit the ground at the same time. How about that? And that proves that Mr. Galileo was correct in his findings.
Superb, Dave.
Well, I always say there's nothing like a little science on the Moon.
Yeah, I mean, it's laughable what is, tried to pass off as, and you know what's so great now about YouTube and about these video platforms is, back in the day, you got one shot to see this stuff on television, and that was it. I mean, you believed it was true. You saw it once. Maybe you saw it on a rerun. Maybe on the other news channel they would rerun some of this footage. But now it's all been released, and people have the ability to look at it and to pick it apart and to really think about it. Like we talked earlier about the lunar landing. Now that people have the technology at their fingertips on their laptops to be able to speed up the lunar landing footage. You have the land rover going around, and you have the guys hopping around in slow motion. Speed that up 200%, and it looks like they went out in the desert and filmed that. But here's something that I'm going to tell you as a video guy. Here's why I believe that the lunar landing was faked. Because there is no way you can have a power source that strong at that time in history, and there's no way you could transmit that video signal all the way to Earth. Absolutely 100% not. Let me tell you something. I have if I have a handheld video camera, and I want, and let's say I'm shooting a scene, and the producer wants to see what I'm shooting. So they have a transmitter in their hand, and they have a battery on my camera. The battery that I have is about the size of a brick. It's more square, but it's about the same mass as a brick. And it only lasts for maybe an hour and a half. And that signal only goes a couple hundred feet. Now you're going to tell me that on that teeny little spaceship, with that teeny little camera, they're going to have enough power to transmit a full color video signal all the way down to Earth. And I can also tell you this, that when they promised a full color video signal, the station that broadcasted the lunar landing, they were pissed because they weren't getting raw video feed. What they were getting was called a kineoscope. And for those of you who don't know what that is, that was an editing process used up until the late 1990s. And I've actually seen the kineoscope technology and utilized it when I worked in a film lab, and it's very interesting. Basically, it's an editing tool. So you have a screen, basically it's a television screen, and you shoot that with a film camera. So now it's on 16 millimeter film. So what they did with those videos, in theory, why you see a black and white image of the lunar landing, although they claim the full color videos exist, was what NASA says they did was transmitted the full color video signal, filmed it on a kinescope, black and white on 16 millimeter film, and then released that to the networks. So therefore, it was not a live event, because to get film processed, it takes hours, and it's a whole process that generally takes about 6 hours to complete, even with the most efficient film laboratories. So why would they get this crappy, grainy, black and white film image when they could have broadcasted color, which at the time the networks were pissed that they didn't have the ability to do, that NASA denied them? But anyway, that's neither here nor there. The whole kinescope thing, that's a side note. My thing is, there is no way with that technology and with batteries being as big and as weak and as heavy as they were, you could have broadcast that signal from the moon. Impossible.
Because honestly, as an RF engineer, I look at this now and I'm like, how in the hell did I miss this? Well, I missed it because of my indoctrinated thinking, just like I missed the impossibility of 60 to 100 mile microwave shots because of an alleged curvature of the Earth. We were making them, but the curvature of the Earth absolutely prohibits that from happening. Something I never thought about, something I guarantee you that no other RF engineer has thought about, or if they have, then they're probably not going to be going to their boss and telling them, hey, we got a problem here, this shouldn't be working, because they'd probably be fired. You know, I'm sure you all understand how that works. All right, so the next thing we're going to do is, because we're not dealing in watts, which we're so used to using in our transmit power, we're going to be converting watts into decibels, okay? Now, you have two basic figures that are used in decibels. You have dBm, which means decibels with reference to 1 milliwatt, which is 1/1000th of a watt, and then you just have simple just dB, okay, which dB watts, which would be the watts, okay. So basically, if we have 1 dB, it's basically, there's basically a 30 decibel difference, okay, between dBm and dBw. So if we say 30, goes back to 0. 30 dBm is 0 dBw, okay. And this is gonna get really clear here in just a minute. So what I'm going to do, first of all, is we're going to take this free space loss calculator, and we're going to find out how much power we have to be able to transmit over certain distances, okay? And again, this is all handy dandy, it's wonderful, all calculated for us. And as you can tell here, I have already done a calculation of 250,000 miles, and I'm sure anybody that thinks about that, that would be equal to a one-way trip to the moon. All right, now hams cannot put any more than 2,000 watts. They are limited to 2,000 watts, okay? And they may be able to get a gain figure of 6 to 9 dB. So again, going back to our rule of thumb, if we have 2,000 watts maximum power input, which gives us maybe 1,500 watts at best output, and we give that through 9 dB, so we're tripling that power. So we go 1,500 watts to 3,000 watts is 3 dB, 3,000 watts to 6,000 watts is 6 dB, and 6,000 watts to 12,000 watts is 9 dB. So we have 12,000 watts ERP, all right? All right, so basically what this is saying is this is a 70 dB maximum power output, even with the best of circumstances. So let's go back to this. Transmitter gain, 70 dB. All right, receiver gain, let's give it I don't know, let's give it that same 9 dB. Calculate it. free space path loss is 108 decibels, okay? So what does that mean? That means to overcome this 108 dB loss of power, now we have to go to dBW, and let's put in 108, convert it. That means that we have to have a transmit power, and you can see this is a big number, 448,734. So we're talking about 63 billion, 95,734,448 watts.
Jeez.
Just to overcome the path loss. All right? Do you see a problem here? And this is only going one way to the moon. All right? Now let's look at something really ridiculous. Okay? Let's look at a distance, and let's all of a sudden now let's go to NASA's frequencies, and let's go to 10 gigahertz. All right? And let's say that they're transmitting, oh, I don't know. And then we know the satellites can't put out a whole lot of power because they only have solar arrays on them. So let's say those solar arrays maybe are capable of delivering, let's say, 10,000 watts, which is absurd. You know, we can just apply a little bit of common sense here to this. All right. So transmitter gain, again, let's give them the benefit of the doubt and say that they can run 10 kW. That's going to be 70 dB, all right? So 70 dB, and now let's go to, I don't know, let's go to the sun, all right? The sun, and the reason the sun is not an unreasonable example because what, Jupiter is a lot further away, right? Stuff like that. So let's just do a shot to the sun. 93 million miles, 10 gigahertz. There's our power. Let's give them the advantage of having a high gain receiver antenna, and let's give them let's give them 20 dB of gain there. All right, calculate. Now we're talking about a free space path loss of 185.9 decibels. Well, let's go back to our decibel converter. So let's go 185 dB. Which means that to make the trip to the sun, now we have to have, oh my, this is such a big number, I don't even know what it is, but it's in the petawatts, okay? You're getting the idea here, guys. In other words, there is no freaking way on God's green earth that we can be making transmissions of these distances given the idea of how much power is on board these satellites. All right, I think, and of course there are other factors. Yes, there are other losses, there are other gains, whatever. But this is a very, trimmed down version to simply show you, even if I'm off by a factor of 1 million or even 1 billion, it's impossible. It is impossible to make these journeys at these distances. Okay, this is the point that I've been talking about all these times. I have just used all mainstream sources, all mainstream information, everything, and I have shown, even in a physics lecture, how all of this works, the impossibility of transmitting a signal. It can't even be done to the moon, all right? Especially with what the hams can do. So what are the ham radio operators talking about when they say, well, we're doing these EME bounces? Well, first of all, EME bounce, if you're talking about a 250,000 mile trip, that means that you've got a 500,000 mile or 500,000 mile journey, that this limited power that the hams can use to go up there and bounce back. As I've just shown, this is patently impossible. So what is it that they're bouncing these signals off of? Well, there's something that reflects RF radio waves. You can call it the ionosphere, whatever you want to call it. That is what it is that is reflecting these signals back. So yes, they honestly do believe that they're doing it, but as I have just shown, using all mainstream calculations and all mainstream science, the impossibility of it goes beyond silly, right? I mean, there's just no way that we can make these types of broadcasts, and common sense tells you that here on good old plain Earth, because if we have 50,000 watts and a relatively high gain antenna for AM radio station KOA, and we can barely cover the state. All right? Now we're starting to put things in perspective. All right? This is what I have been trying to tell people. And again, there are several other factors, but believe me, nothing that's going to make a million or a billion times difference in these calculations. Do the calculations yourself. Look up antenna gain factors, and also how far down in the mud or signals can be retrieved from ground noise level. And typically, a typical receiver sensitivity is minus 100 dBm, okay? So that's typical, some a little more, some a little less, depending on the frequency again. All these are factors, but the bottom line is that no matter what frequency they're using, and they would be far better off using low frequencies than they would be microwave, but even they won't make the distance, even though they have considerably less path loss.
I'd go to the moon in a nanosecond. The problem is we don't have the technology to do that anymore. We used to, but we destroyed that technology, and it's a painful process to build it back again.